Hi everyone, this is Yuchen. I'm so excited to give my first paper presentation here and share this work, PrivateFL, to you guys today. And this is a joint work with Haolin, Dr. Yinzhi from Johns Hopkins University, and Dr. Gong from Duke University. So before we get started, let's see the brief outline here. And the first part I'm going to introduce is the background of differential privacy and federated learning. So federated learning is a collaborative learning framework which allows many clients to learn together while using their own data without sharing the data with each other. So the key benefits of federated learning is the data privacy. And there are three main steps here. The first step is each client first train the local models on their local data. And the second step is the clients will upload the local models to the server, and the server will aggregate all the local models as a global model. And the third step is each client downloads the global model as the next round's initial local model. And federated learning has been deployed as many areas, like for example, the mobile phone, the finance, and also the healthcare, and also Internet of Things. However, there are always some challenges here. And the first challenge is data heterogeneity will cause federated learning inaccurate. So just as this figure shows, if we assume client A has training data as cat and client B has trained data as dog, and if we let them just train separately using their own data and just simply average them together, and the global model will not perform good on client A and client B's data. And this is the data heterogeneity. And the second one is the privacy leakage. Although federated learning can provide some privacy, but it's still vulnerable to some privacy attacks. For example, the membership inference attack. So in the membership inference attack, either a malicious client or a malicious server can infer the training data information from the victim client. And one de facto approach to defend against those privacy attacks is differential privacy. So when we apply differential privacy to federated learning, there are three main variants. The first one is local DP, short as LDP. So in LDP, it used DP SGD to replace the normal SGD and to add noises on the gradient during the training. And the LDP can defend against both untrusted server and untrusted clients. And the second one is distributed DP. So distributed DP added noise also at the local end, but the noise is added after the local training. The noise is added on the local model, and the server also use a secure aggregation to enhance the privacy. And the third one is central DP, short as CDP. So CDP add noises on the summation of the local model. So CDP can only defend against untrusted clients, but not the untrusted server, since the server can get access to the raw model without perturbation. And the next part is the challenge, which is the accuracy degradation. So as we discussed before, federated learning becomes inaccurate when the data distribution is heterogeneous, and differential privacy encounters accuracy degradation because of the added perturbations. And when we combine them together, one interesting finding is that we find, although the data is IID for federated learning, when we add differential privacy to the federated learning, the accuracy degradation is much more severe than when we add differential privacy to centralized learning. So why that happens? And we find that it is because the differential privacy introduces additional heterogeneity to federated learning. And we will explain it in details for LDP, CDP, and DDP in the following three slides. So first part is LDP-induced heterogeneity. So recall that LDP used DP SGD, which add different noises to different clients, and thus noises will bring more heterogeneity. And also, when we use DPSGD, it also does the gradient clipping, and which will cause the clipping bias and also more heterogeneity. And here we have an experiments on CFR10 and MNIST data sets. And we can see that when we have a small epsilon, which is the privacy budget for differential privacy, a smaller epsilon means a high privacy level and which require more noises, and thus the heterogeneity level is higher there. And here we also have to stabilize to represent the non-private training as a reference. And we can see that LDP do increase the heterogeneity compared with non-private training. And the second one is DDP. So similar as LDP, DDP's noise is also added locally. So here we have a similar observation that DDP will introduce heterogeneity to LDP, and a smaller epsilon will bring more heterogeneity here. And the third one is CDP. So different from the previous two, the CDP's noises is added uniformly on the server end. However, we find that when the client's data is heterogeneous, the same noise will be diversified the client data, which introduce more heterogeneity to the Federated learning system. And we observe that if we have a higher privacy level, the heterogeneity will also become larger here. But different from LDP and DDP, the amount of heterogeneity is less than LDP and DDP because the noises is added uniformly at the server. And also, if the data distribution is IID, then we find that CDP will not introduce much heterogeneity in this scenario. And next part is our solution, personalized data transformation. So the idea is we add one linear layer in front of each client's local model, and we name this layer personalized transformation T. And this layer is trained with local model, but when the client is communicating with the server, this layer is always kept locally to shift the heterogeneity. And why we need the personalized transformation? So looking at this figure, assume now we have a non-convex learning problem, fx equals to cosine wx, and we have two clients participating in the Federated learning here, and each of them has a synthetic data perturbed by different Gaussian noises. And so currently we can see that those two lines are far away from each other because the distribution of losses are different. And the client B has an optimal weight as 4, and that for client A is 6. So if we just average them together as the Fed average does, we will have a 5. And we can notice that this 5, if we use this 5 as the global model, both client A and client B will suffer from a very high loss. And now if we use personalized transformation for both client A and client B, we can notice that the heterogeneity between two clients is reduced, and those two lines becomes aligned with each other, and then we will have a good global model. And the next question is, what transformation functions do we need? Since the function spaces are infinite, so we compare 4 categories, which is one-to-one versus many-to-one, and also linear function versus non-linear function. And looking at this table, among all the candidates, we find that the one-to-one linear function, which is alpha x plus beta, with 2 learnable parameters, has the highest accuracy because this function can reserve the original sample's separabilities, and more empirical analysis could be found in our paper. And the next part is the evaluation. So the first research question is the accuracy improvement on Federated learning with differential privacy. So we compare our PrivateFL with Fed average on 6 data sets. and 5 of them are image data sets, and 1 of them are non-image data sets. And we observe that our method outperforms Fed average among all the data sets continuously, and also from an average 2 to 3% accuracy improvement to 34% accuracy improvement. And the second question is the accuracy of Federated learning with DP improvement methods. So we find that our method can also be combined with existing DP improvement method and brings further improvement here. So here we compare and added our method to data normalization, which is a 2021 ICLR paper. So this paper used the data normalization method to normalize the features extracted from large pre-trained models to help the differential privacy in centralized learning. So here we have ResNext on CPR100 and SimCLR on ImageNet, and also Clip on public data. And we can observe that compared with using data normalization alone, we have a 30% gap between non-private and private training. Our method can reduce that to 5%, and also for Clip, we can see that our method can reduce that gap to 0.4%. And the third research question is the accuracy improvement on different data distributions. So we observed that our method can improve the model's accuracy with data from non-IID distribution to IID distribution. And second, we find that the accuracy improvement on non-IID distribution is larger than that under IID distribution. The reason is that our method can not only reduce the heterogeneity for DP, but also reduce the heterogeneity for data itself if there is some heterogeneity. And the last research question is the accuracy on different scalabilities. So we observe that our method can continuously improve the accuracy for different number of clients. Here, we observe that the 50 clients have the same improvement with the 500 clients. Okay, so let's move on to the summary. So we have we've highlighted 4 contributions in these slides, and the first one is we observe the correlation between Federated learning heterogeneity and differential privacy accuracy. And the second one is we propose a novel approach named personalized data transformation to solve this problem. And the third is our method can be combined with personalized Federated learning method and also DP improvement method to bring further improvements. And the last one is our work is open source at this link, and our work has been passed the artifact evaluation and has been awarded for 3 badges. So please feel free to check it out if you're interested. Thank you. Any questions?